We'll continue this morning session, and our next speaker is Stuart, University of Warwick. The title of his talk is SPDE limits, please. SPDE limits for Metropolis-Hastings methods.
Is that volume okay? What I'm going to talk about is trying to draw samples from measures on function space. And in particular, the question that I want to address is what is the computational complexity of drawing samples from measures on function space? And I will be looking at the use of Monte Carlo Markov chain methods to sample the measures. And I will use diffusion limits of the Monte Carlo Markov chains, which will be diffusion limits to SPDEs, to quantify the computational complexity. The kind of applications I have in mind come from inverse problems, many of them in differential equations. And the inverse problems are formulated using a Bayesian perspective, which gives rise to a probability measure for functions. So let me just state more precisely what the aim of the talk is. So I'm going to have some measure mu, which is determined via a density with respect to a simpler measure mu0 with Radon-Nikodym derivative, which I'll write as the exponential of minus a potential phi. And for simplicity, just think of u as being in R infinity. Although if you like to think of u as representing a function, you can think of these as the coefficients of an expansion for the function in a Fourier basis or some other basis determined by a Cahunen-Loewe expansion, something of that type. And mu0, I'm going to assume, has a product structure. So specifically, mu0 du, I'll write as a product from 1 to infinity of some scale factors lambda j, f of uj over lambda j du. So this means that mu0 has a product structure, and in each component, up to a scaling, each component ui, uj, u2, u3, uj are distributed identically up to scaling by lambda j. So these lambda j's are the standard deviations of each component in this measure. So if you want to think of an example to carry in the back of your mind throughout the talk, which will be an appropriate one for many of the applications I'm interested in, that will be the case where this is a Gaussian measure, and then f of u is just e to the minus u squared over 2. Okay, and then the objective is that what I would like to do is draw samples from this measure. And at some point, to make a computational algorithm out of this, I'm going to have to finite dimensionalize this. So R infinity will get replaced by Rd for some large d. And the question of interest is how much computational work do we have to do to draw enough samples from this measure to effectively describe it. Okay? So in a moment, I'll come back and write down some assumptions on phi and on the measure mu0. But I won't go straight into them because I just want to give you an overview of where I'm going to go. I just don't want to get straight into writing down technical assumptions. What I'll do after that is show you how to finite dimensionalize this problem and replace it by an appropriate approximate problem on Rd. So we'll work on an approximate problem in Rd, and then I will introduce for the problem on Rd the idea of random walk metropolis. This will be a Markov chain which will be constructed so that it has an invariant measure which is close to the measure mu that we want to sample. So that if we generate sample paths from this discrete time Markov chain, they will approximately solve the problem of sampling from mu. Okay. Then what I'll show you, that this algorithm that I'll write down will have many parameters in it, and I will come to a discussion of the choice of parameters. And make some statements about how to choose them in such a way as to make an effective algorithm. And then to substantiate the claims that I'll make about the computational complexity that arise from these choice of parameters, I will derive an SPDE or diffusion limit for the discrete time Markov chain. So we'll interpolate the discrete time Markov chain into a continuous time process and show that that converges to an SPDE. So in terms of the connection with this overall themes of this conference, the key role of the stochastic partial differential equation is in enabling us to quantify the effect or the cost of algorithms for sampling measures on infinite dimensional spaces. Okay, so that's the objective. As I said at the beginning, just to repeat, the motivation for problems of this type is in carrying out the framework of Bayesian statistics for functions. So there are many inverse problems in partial differential equations where one is trying to find a function, but the inverse problems are ill-posed. So you might look at, for example, determining the initial condition for Navier-Stokes equations from observations of the solution, say pointwise observations of the velocity field at positive times. These inverse problems for initial condition for a PDE, which is dissipative, they're ill-posed, and a good way of regularizing them is through Bayesian statistics, and that gives rise to the need to sample probability measures given by a structure of this form here, where mu0 will be a prior measure incorporating regularity information about the functions. Phi would be something that would incorporate information about the observations, and mu is the posterior measure that we're interested in sampling. Okay, so that's where they come from. And the assumptions I'm about to write down are motivated by those kind of applications. So they're not just drawn out of the air to make the theory work. They're assumptions which are natural for the applications of interest. So first of all, let me introduce some spaces on R infinity. So I'm going to let HS be the Sobolev space of functions U in R infinity, such that j to the 2s uj squared is finite. And then H0, of course, which I'll just denote by H later on in the talk, is just little L2. And I will assume that the prior measure, mu0, the reference measure, is such that mu0 of HL is 1, by which I mean that if I pick a function at random from the prior measure, it will have regularity to put it in the space HL. And then I need to make some assumption about the phi that determines the change of measure and relate it to the properties of mu0. And the kind of assumptions that work well in applications of interest to me are, first of all, I'll assume that phi is positive. This is not necessary, but it's just simplest case to deal with for now. I'll assume that we have some Lipschitz condition on phi in a space So this is the norm on the space HS. And this is assumed to hold for some s less than L. And this is for all, it's a local Lipschitz condition with U and V in the space HS bounded by R. So Lipschitz constant depend on R. And this will be for some s less than L. Well, phi is scalar valued, so this is just the modulus. So if you want to think of an example of this setup here, for example, you can think of mu0 as being Brownian bridge measure, and phi being the change of measure that you get from the Gasanov theorem, so that mu is Ornstein-Uhlenbeck bridge measure. That would be an example which satisfies these conditions, with s up to a half and L being 0, for example. So there are many, many examples that fit into this framework. And I should say I want to make some assumptions which I haven't written on the eigenvalues, the standard deviations. So I'll assume that for some k, j to the k at lambda j, well, roughly speaking, that lambda j behaves like j to the minus k. So, for example, if mu0 were Brownian bridge, then k would be 1, and and if phi was such that mu were Ornstein-Uhlenbeck bridge, then this condition would be satisfied with s is 0, and L being any number up to 1/2, not 1/2. Okay, so are there any questions about the setup? Okay. Well, welcome interruptions if you have any questions. Okay, so what I want to talk about now, so this is an infinite dimensional problem. I'd like to get information from this probability measure, but it's on R infinity, so I need to finite dimensionalize. And the way I'll do that, and this is just prototypical of many things one could do that are more complicated, but what I'm going to basically do is just truncate U after D terms. So I'll introduce a projection PD which acts on U by just setting everything to 0 after the dth element in this vector in R infinity, and then I introduce a new measure mu D, where the change of measure is given by phi applied to PD U. So this measure, if D is large, intuitively should approximate the measure mu. And indeed it does. So let me just state a simple lemma of prototypical of what's available. And this is in joint work with Simon Cotter and Musume Dashti and myself. Under some assumptions, which I'm not going to write in details, but they are related to the growth of L with respect to R and the assumptions on the choice of F. For example, if mu is a Gaussian measure, then one has a Fanique theorem, and if L of R grows polynomially, then the following theorem would hold, that if you look at the Hellinger distance between the two measures mu and mu D, then it's bounded by a constant divided by D to the L minus S. Okay, so that's a statement that says that the error that you make is related, think of D as large, of course, is related to how big L is. So the larger L is, the more regular functions are which are drawn from the prior measure, and how big S is, which is the space in which you have control over the change in measure. So this tells you that this measure that I've written down, which in a way that I'll show you in a moment is essentially finite dimensional, this measure is mu d is a good approximation of mu. Okay? That motivates sampling mu d rather than mu, and using samples from mu d to get approximations to samples from mu. I should say the closeness in the Hellinger, if you're epsilon close in the Hellinger distance, then you are, for those of you not familiar with it, then you are also epsilon close in expectations of functions which are square integrable. Okay, so this closeness in this metric will mean that expectations of functions calculated against mu d will be close to expectations against mu. Okay, so this essentially finite dimensionalizes our problem in the following way. If you look at mu d, so on the complement of the projection PD applied to R infinity, mu d is just equal to the prior measure, the product, the measure mu 0, which has product structure. So that I assume that we understand and know how to deal with. So that's the infinite dimensional part of the problem. On the finite dimensional part, mu d, it was just, well, the finite dimensional part is you can think of as being equivalent to just Rd. Here mu d has Lebesgue density pi d, and I'll write pi d on the board over here. So pi d is just what you get by finite dimensionalizing this, replacing this by something that only depends on the first d coordinates. So pi d is Lebesgue density, which is proportional to e to the minus something I'll call phi d of u, pi 0 of u. And now here I'm thinking of u as being in Rd. Pi 0 is just the truncation of this to d terms. So pi 0 of u is just this density. And phi d of u is just phi evaluated on the vector, which is 0 after the dth term. Okay, so I finite dimensionalized the problem, now working on, on a density on Rd, which is made up of the individual densities on the first d terms, first d coordinates. And I've replaced phi by a function phi d, which is defined simply by taking phi and setting u to be 0 after the dth entry. And this is a reasonable thing to do because of the regularity which is implied by the assumptions over here. Yeah.
Some growth on L on this Lipschitz constant.
Yes, sorry. So that
the Hellinger distance.
no, that's what I was saying here. So if I haven't written all the conditions. So if mu is a Gaussian measure, you have the Fanique theorem, and what you need to be able to do is integrate this. So for example, in the case where mu is Gaussian and this is polynomial, in fact, anything that you can hit with the Fanique theorem. But if you had a different measure here, then you would make different assumptions. Okay, any other questions? Okay, so we have this set up. What I want to do now is describe to you the random walk Metropolis algorithm. So this is prototypical of many what are called Monte Carlo Markov chain methods, which I'm sure many of you are familiar with. But for those of you that aren't, just to repeat what I said at the beginning, the basic idea of these methods is, of Monte Carlo Markov chain methods, is the following. Given a density that you wish to sample from, you construct a Markov chain which is reversible with respect to the measure associated with that density. And then, assuming ergodicity, samples from that Markov chain will approximately sample the measure you're interested in. I'm going to describe one particular algorithm, which is random walk Metropolis method. But the methodology that we're using is much more general than that applied to this specific problem. So the idea of random walk Metropolis is this. So I want to construct a Markov chain UN, which is for which this density pi d is invariant. One thing I should say as well, just to streamline the talk, I will sometimes be using u in R infinity and sometimes in RD. Can always, and I should be a bit lax about describing how I move between these. So just let me say a word about that before I go on. To go from something in R infinity to something in RD, I will just apply the projection that sets all the components to 0 after the dth one. To move back from something in RD to something in R infinity, I will just append zeros on the vector from d plus 1th entry up to infinity. So in that way I can move backwards and forwards between these two descriptions. But presently, so these UN, each UN here is in RD. And the idea to construct this Markov chain, you can write down succinctly as follows. Given UN, I'm going to propose a new element of this Markov chain, which will become UN plus 1 if it's accepted. And I propose it in the following way. I'll just do a symmetric random walk with covariance operator A and scaling factor 2 delta. So psi n here is a Gaussian with mean 0 and identity covariance. And then the idea of the Metropolis algorithm is to choose UN plus 1 to be equal to Vn with some probability, which I'll describe in a moment, and with the remaining probability to have the chain stay where it's currently located. Okay, so gamma n is going to be 0 or 1. If gamma n is 1, then the n plus 1th element of the chain is given by Vn. If gamma n is 0, then we stay where we are. The n plus 1th entry of the chain is equal to the nth entry of the chain. And gamma n is a random variable, which can be given as the indicator function of omega n. Omega n is going to be a uniform random variable in 0, 1, which is orthogonal to psi n, independent of psi n. And so we just ask the indicator function omega n is in 0 an, where an is given by the minimum of 1 and the ratio of pi d, which is our target density evaluated at Vn, divided by pi d evaluated at Un. So if you haven't seen this before, let me decode it for you. It's a very straightforward idea, which you can see heuristically in the following way. If you want to, you'd like the Markov chain to spend time where pi d is large. That's where most of the probability is. And you notice that if the proposed move, Vn, gives rise to pi d, density, which is larger than the density at the current position, this ratio is 1, and then an is 1. And if an is 1, you pick a uniform random variable in 0, 1. This indicator function will be 1, which will mean that un plus 1 will equal Vn. So if your proposed move increases the probability relative to your current state, then you accept that move. If it decreases the probability, then you will only accept the move with some probability, governed by the ratio of pi d at the proposed state to pi d at the current state. Okay. Yeah.
A is the matrix related to the lambdas?
No, A is a scalar. So this A, oh sorry, that A.
Yeah.
Right. So I'm going to talk about it when we get to the choice of parameters section. I'm going to talk about how to choose delta, which is a scalar, thank you, and A, which is a matrix. Thanks. So delta is going to be positive number, and A is going to be a d by d positive definite symmetric matrix. Thanks.
And the pi d is also reversible, right?
This Markov chain is reversible with respect to pi d. Yes. So that's the that was the basic Metropolis idea, which has many variants, but this is the basic plain vanilla version, which I'm going to study. Thanks. So yeah, the UN that you generate in this way, assuming ergodicity, this sequence here will be distributed according to a measure with density pi d. Okay, so this is when you first see this idea, if you haven't seen it before, it looks amazingly powerful, which it is. But on the other hand, there's a lot hidden in this. To make this actually work in practice, to state it in simple terms, what makes this hard to use in practice for high-dimensional problems is that typically AN is tiny. I'll quantify that in a second. But unless you choose delta and the matrix A carefully, then AN will tend to be exponentially small in some measure of the dimension of the space. You will reject all the time, and the Markov chain, although in principle pi d invariant, will spend vast amounts of time stuck in one state. It will not be an effective algorithm. So the challenge in making this an effective algorithm is the question of how to choose the parameters delta and A to make this work in a way that's reasonably efficient. Okay. So that's what I want to talk about now is the choice of the parameters. So just to complete this, to make this reversible with respect to pi d, I've said already that psi n and omega n are independent of one another, and then one chooses them independently at each innovation of the Markov chain. Okay, so let me talk a little bit about the choice of parameters now. So I'll write lemma 2. I'm going to write lemma 3 in the same place in a second. So this is a result with Alex Beskos, Gareth Roberts, and myself. And it concerns how to choose these parameters, delta and A. So first of all, let's concentrate on the choice of delta. The basic thing that I described a moment ago, the phenomenon that AN will tend to be tiny, can be controlled by choosing delta to be small. And the appropriate scale for delta turns out to be algebraic powers of the dimension d. So we can choose delta to be L squared, which is just going to be some positive scalar, d to the minus rho. And I'm going to investigate how we should choose rho to make this algorithm work sensibly. And I will, in this case, choose A, first of all, to be the identity. I'll come back to a better choice in a moment. If we do this, then do I need to say anything else on this? That's everything I want to say. Okay, so if we choose rho to be greater than or equal to 2k plus 1, then okay, what governs whether or not you make moves in this Markov chain is A. Because we're going to pick to make a move, gamma n has to be 1, and gamma n is the indicator function of a uniform random variable in the interval from 0 to an. So what you'd like is that this an, you'd like an to be of order 1 with respect to the dimension d. Okay? And that's what happens if you choose a row sufficiently large. The expected value of an is of order 1. And in fact, if it equals 2k plus 1, it's equal to the expected value is a number which is neither 0 nor 1. If it's bigger than 2k plus 1, it will actually tend to 1 as d goes to infinity. On the other hand, if you choose rho to be smaller than 2k plus 1, that is, if you don't choose this delta to be small enough, then the expected value of an, I mean, heuristically one expects this to be exponentially small. What we can prove is that it's bounded by some constant times d to the minus p as d goes to infinity for any p. I think with hard work you could show that it's actually exponentially small. So there's a sharp cutoff here. If you choose rho to be 2k plus 1, let me remind you what k is. Sorry, k is related to the standard deviations in the prior measure. Lambda j is like j to the minus k. There's a sharp cutoff here in that if you choose rho to be 2k plus 1, you'll get an order 1 acceptance probability uniformly as the dimension tends to infinity. Whereas if you choose rho any smaller, that is, you try and choose larger steps, you try and make larger increments, then you will reject with what heuristically you can think of as exponentially bad probability with respect to the dimension. And what we can prove is what's stated here. Algebraic, it's worse than any power.
In the definition of an,
Yes.
you wrote pi d at dn. Is this density calculated?
This is the density, yes. So pi d.
So this is this exponent.
Yes, so pi d is the density which gives us an approximation to the measure mu, and it is given as a change of measure from a product measure pi 0. So that's the density we're trying to draw samples from. Did I answer the right question?
Okay. Yeah.
And where does the row appear in the algorithm?
Rho doesn't appear in the algorithm other than it's telling me how I'm choosing delta if I were to try and solve this problem on a sequence of problems of increasing dimension. So roughly this says that as I increase the dimension, I'll have to decrease delta, which is the size of the move. And what this is saying is that if I try and decrease delta too slowly, I'll reject all the time. If I decrease delta at rate d to the minus 2k plus 1, then I will get an acceptance probability which is of order 1.
A row is the exponent of d to the minus rho? Oh,
Yeah,
I see.
rho is. Okay, so why is this interesting? Well, the rough heuristic that is related to what I've described to you here is that the amount of work that you need to do to explore pi d is inversely proportional to delta. This is a heuristic which is useful, and I'm going to justify it in a bit later. The number of steps that you need to effectively sample the measure you're interested in pi d is roughly, in terms of d, grows like the inverse of delta. So one would like delta to be as large as possible. Say that another way, as you know, the asymptotic variance in Markov chains is governed by the rate of decay of the correlation functions, and the larger the moves you make, the better the decorrelation in the Markov chain. So So you'd like delta to be as large as possible, because then the number of steps you require to sample the measure is smaller. The problem is, if you choose delta to be too large, as in the second part of the theorem, you'll reject all the time, exponentially often, roughly. But if you choose delta just right, as big as you possibly can, but consistent with the acceptance probability being of order 1, you will make the largest possible moves you can make consistent with them being accepted, say, half of the time. Yeah?
Did you tell us what A was going, capital A was going to be?
No, so I haven't come to that. So now, here A is the identity. I'm now going to refine this result where I choose A a bit better. And so let's turn to that now. So these lambda j's are standard deviations. And if I choose A to be the identity, as I've done here, I've not built in any knowledge about what happens in the prior measure with regard to how things change as you scale the dimension. I can build that in if I construct a matrix CD, which is a diagonal matrix with variances given by the squares of the lambdas. Now, I should say something about this. Although I'm doing everything in coordinates where mu0 is explicitly a product measure, in terms of the implementation of the algorithms, Gaussian measures are always product measures if you work in a Calhoun and Lerver basis. And that's why we do the analysis. But that does not mean that the algorithm that I'm stating needs to be implemented in the Calhoun and Lerver basis. Indeed, in applications, you typically would not want to do that. And so when I write down CD as a diagonal matrix, that's because I'm working in those coordinates for the purposes of the proofs. When we implement the algorithm, CD will be an appropriate truncation of the covariance operator of mu0, the reference measure. So if we choose this better choice for A, which essentially puts the size of the moves that we make on the right scale, governed by our assumptions about the reference measure mu0, then this improves considerably. We remove k, and we can get, instead of rho having to be 2k plus 1 to get an order 1 acceptance probability, rho can be of order 1. In terms of computational complexity, so let's think of Brownian motion case, Brownian bridge case in one dimension. So the k is just 1 in that case. So this is a difference between choosing a step which scales like d to the minus 3 as opposed to a step which scales like d to the minus 1. Okay. So that's an order of magnitude improvement by choosing A in this way. However, okay, when A is diagonal, you can and should always choose, when you're working in diagonal coordinates where everything is diagonalized, you can and should always choose this choice. On the other hand, if you're working in a general setup, you'd have to calculate the square root of C, and there's computational complexity associated with that would depend on the particular problem that you were solving. So there are computational issues related to the complexity I'm talking about over and above the total number of steps, which is what I'm focusing on in this talk. Okay, so that's lemmas 2 and 3. I think that's what I wanted to say about choice of parameters. So the rough heuristic I've given is what's written here. This heuristic holds if the expected acceptance probability is of order 1. As the dimension goes to infinity, then what you should expect, and I'm going to substantiate that now with diffusion limit, is that the number of steps that you require to explore the measure will be proportional to 1 over delta. Yeah?
My apologies. All the things that you're saying are relative to the case where you can write a product measure from u0, or?
Yes. But a product measure includes any Gaussian measure, sure. And I don't have to work in the Calhoun and Lerver coordinates. But yes, the reference measure is always product.
Excuse me.
Yeah.
Perhaps you said already, but so lambda k is like k, for instance, you said in
Yeah, so lambda
it's growing.
lambda j is going like 1 over j to the k.
Okay.
So for example, k is 1. These are what you get for Brownian bridge or Brownian motion. So most of the problems I'm interested in C is fractional negative power of a differential operator. So in the case of Brownian bridge, C is the inverse of a second order differential operator with Dirichlet boundary conditions. And if you had Ornstein-Uhlenbeck bridge, which would give rise to a quadratic here, then you'd have a similar setup. Any other questions? Okay, so what I want to do is substantiate this idea. So if the average acceptance probability is of order 1, then roughly, let's say it's a half, then every other step you accept a move, and you move somewhere. And what I'm claiming is that then the amount of steps you'd have to take to effectively describe this measure is inversely proportional to this delta, which appears here. And the way to see that is what I'm about to describe to you now, which is to look at a diffusion limit for this Markov chain, where I'm going to interpolate it into a continuous time process with a scale and relate that continuous time process to a stochastic PDE, which is invariant for mu. And that will give us this justification of this heuristic. If the expected value is exponentially small, then the cost becomes exponentially large. So you never want to go out of this regime. And you want to choose the smallest possible row consistent with having an acceptance probability of order 1. Okay, so let me just write diffusion limits, because first of all I'll tell you about some earlier work due to Gareth Roberts and co-workers. It's about 10 years old, on just scalar SDE limits. And then I'll go on to the SPDE limit. The basic thing I want to do, so that the picture is, I'm going to take this discrete time Markov chain, which will give rise to, so here's UN, it'll give rise to a sequence of samples, and I'm going to interpolate these to get a piecewise linear function. And the scale here is 1 over d. So you think, so this now is there's a time here, and the interpolant I will call Zn, or Zn, for those of you who want to have it that way. And this, so what this says is that the effective time step of this continuous time interpolant is 1 over d. And the basic gist of what I'm about to show you is that this process will converge to the sample path, or, well, it will converge in the sense of weak convergence to a process whose sample paths are given by a diffusion, an SDE. And because to get to time of order 1 in the SDE, we require d steps of length 1 over d, that will quantify this idea that the amount of work is inversely proportional to the step. So for everything I'm about to do now, delta is going to be order 1 over d. And that choice will follow from this lemma in a couple of cases. Okay, so the continuous time interpolant is a function. Sorry, that n should have been d. It's just the dimension. So the zd of t is this is just the formula for what's written there in pictures. So you don't really need the formula if you believe the picture. So that's a formula for a function, continuous time function, piecewise linear, and when t is equal to n over d, it takes on the values of the Markov chain un. Okay, so at this point, t is n over d. The Markov chain is taking on, this continuous time interpolant has the value un. Okay, so now let me write down, first of all, a scalar. Let me concentrate on the reference measure, first of all. So up to scaling, everything in the reference measure is governed by a single density f. I'm going to write down the Langevin equation, which is invariant for that density on R. And h of L is just some number, which I'll come back to in a moment. So here, so this is f of z. So this is z in R, and W is a standard Brownian motion on R. And this thing is invariant for the measure with density f. Okay, so the first result I want to tell you about, which is due to Roberts, Gelman and Gilkes from 97, concerns the case where phi is 0, so the measure you're sampling is simply a product measure, and k is 0, so it's in fact an IID product measure. The lambdas, well, it's by k is 0, I just mean the case where lambda j is identically 1. So all of these, of course you can relax that, but in this case the lambda j's are 1, it's an IID product. So this looks like a kind of weird measure to be interested in sampling. It's just a copy of an infinite set of copies of the same measure. So you actually only need to sample one of them to understand the whole measure because they're independent. However, there's a lot of insight that comes from this, and the key thing to realize is that even if your measure is a product, the accept reject rule in the random walk couples together all the dimensions. So you would never use this algorithm to sample in this case, but as I'm going to show you, the insight that comes from here is useful for non-product cases which are of interest. So bear with the fact that this looks like a strange measure to sample in this way. But the basic gist of their result is that if you take any one component of this interpolant of the Markov chain, so this is a ZD here is a vector in RD. I take one component of it, call that J, D, then that continuous time interpolant of the Markov chain converges weakly to the solution of this SDE. In the space of continuous functions on a finite interval taking values in R. What that tells you is that the continuous time Markov chain behaves like this diffusion here. This diffusion here will have a mixing time, some time that's got nothing to do with the dimension d, that there is no dimension in this problem, it's just a scalar SDE. It will have some time t large enough that a sample path started in equilibrium will have approximately covered the invariant measure by time t. So given that the random walk Metropolis algorithm generates sample paths which are close to those of this diffusion process. The relevant question to ask to gauge complexity is to ask how many steps of the Markov chain do we need to make to get up to this time t, which is a time sufficiently large that we've explored the invariant measure for this stochastic differential equation. And because the time steps are of size 1 over d, that means that the number of steps required is of size d. Okay, so the take-home message from this is that it implies that the number of steps started in equilibrium is of order d. So it quantifies how many steps you need to describe the invariant measure. There are other things of interest in this work. And the second one relates to this constant h of L, which, as you can see here, is just a scale factor which determines the speed at which this diffusion runs. So it's simply scaling time, because it appears that h of L here, square root of h of L there. And L is precisely this number here, the scaling in front of d to the minus, in our case here, rho is 1. So I should have said that in the theorem. So rho is 1. So there's an optimal choice of this parameter L, which maximizes h. And maximizing h maximizes the time scale for this, maximizes the speed for this limiting diffusion process. So in addition to having chosen the scaling correctly, that is to choose rho to be 1, there's a further optimization you can do over this parameter L. And the remarkable fact is that the optimal L, the remarkable fact that came out of this work of Roberts and others, is that the optimal L is equivalent to a particular choice of average acceptance probability, which is a number of about 0.234. So that from a practical point of view, people like this result because it means that if you fiddle with your algorithm so that you achieve an approximate acceptance probability of 0.234, then you will have scaled the algorithm optimally. Okay. Yeah.
So this f is the same f as we had at
This f is the same f as over there. So what I'm doing is I'm looking at the case where phi is 0, so I'm actually sampling a product measure. But I'm doing it with random walk Metropolis, which correlates all of the different dimensions when you do the accept reject. And what this theorem does is quantifies the cost of doing that. Now, you wouldn't want to do that in the product case, but in the non-product case, you don't have any choice. You can't separate the coordinates. Okay, so just again, the key ideas that came out of this work, and their generalizations to other Monte Carlo methods other than the random walk, are that it quantifies the number of steps as being order d, and it gives you a specific acceptance probability which optimizes the rate of convergence. Okay. Remarkably, both of those facts transfer to the non-product case. That's how I'll finish by describing that result. But what makes the non-product case more complicated is that in the non-product case, we can't expect a single component of this continuous time interpolant of the Markov chain to converge to a scalar diffusion process. Everything is correlated. And so in the non-product case, we must expect a diffusion limit to an SPDE for the whole of all of the components of Z. Right, so that's the final result. So the particular SPDE that I'm going to work with is this. And I'm going to work in the case where the reference measure, mu0, is a Gaussian with mean 0 and covariance operator C. And this C is the covariance operator in the reference measure. Okay, so this, I mean, there's a matter of terminology here. You could view this as an ordinary stochastic differential equation in Hilbert space. And in fact, you don't even need mild solutions for this, because just so that you have some intuition, C is a covariance operator, so this is a compact operator. And just as an example, you can think of C as being the inverse of minus Laplacian plus Dirichlet boundary conditions, if you want to think of a specific case. But the point is, C is a covariance operator for a Gaussian measure, so it's nuclear and trace class, and so this will be an example that will fulfill that, and this would correspond to a Brownian bridge prior. But the theory is much more general. That's an example, so you just understand that C is a smoothing operator, and you can think of its inverse as a differential operator or a fractional power of a differential operator. Okay, and then there's a theorem analogous to this, which is joint work with Jonathan Madingley, who's here, Natesh Pillai, who's also at Warwick, and is not here but will be here later today.
Wiener process, what is it?
Yeah, so this is just cylindrical Wiener process, or if you like, the root CW is a Wiener process with covariance operator C, but white in time. Yeah, Wiener, and then the DW is white in time. Okay, so here, now we no longer have phi to be 0. Let's just think of the case where phi is linearly bounded. I'm sure one could relax that, but we haven't done that. K is greater than a half. That's necessary, as you see from this, to make C a nuclear operator, so it's a well-behaved Gaussian measure. And, well, I didn't say, and I should have done, in this work of Roberts, essentially one is choosing A to be 1, rho to be 1. So here we choose A to be C and rho to be 1. And then the continuous interpolant that I describe here, CD. Now this is on RD, but I can lift it up to the Hilbert space just by padding the remainder of the measure with zeros. This thing converges weakly to the solution of this stochastic PDE in the space of continuous functions on 0t, taking values in H, which is H is it's just little L2 if you're working in Fourier coordinates. And so this theorem tells you exactly the same things that the original work of Roberts did 10 years ago, namely that it tells you that it implies that the number of steps to explore pi d grows like d. But perhaps more remarkably, this choice of average acceptance probability maximizes h of L in the same way as it does in the case where the limit is to a scalar diffusion. So the optimal L is given by choosing the algorithm so that the average acceptance probability, as you increase the dimension, is given by this specific number. So that's a quite strong, surprisingly strong result in a way, because as I mentioned, this appears to be quite a strange setup from the point of view of applications, because it's simply dealing with product measures that you would never sample this way. Here we're dealing with non-product measures, and although I didn't give you any applications, I will in June talk about the inverse problems that give rise to these kind of measures. And there are numerous really interesting applications that give rise to this structure with the assumptions that I've written there. And that they're far from being trivial from an applied point of view. And yet, all of the intuition developed here transfers directly to that situation. And the reason why that happens is that is a simple take-home message. The posterior, the measure you're interested in, mu here, is absolutely continuous with respect to mu0. And so all of what that means, roughly speaking, is that if you express u in a Carhoon-Lerver basis, then in the tails of the vector u, not the tails of the probability, the tails of the vector u, the measure mu behaves very much like mu0. So if you're controlling the infinite dimensionality of this problem, when you go out to the infinite dimensional part of the vector u, mu and mu0 look the same. Okay? And that's controlled by this assumption on phi, which basically means that the mu0, the reference measure, dominates the change of measure. And so, in fact, although it might appear initially surprising that one can get so far, it's really not that surprising when you think about it, because in the tails of the vector u, mu and mu0 are very, very similar. That's basically the intuition.
Does this mean that basically you can handle a Ornstein index situation where the underlying is Gaussian, and then you have the linear sort of Lipschitz coefficient of drift, but it's hard to go beyond that?
Well, the theorem I've stated has this being linearly bounded because that makes the technicalities go away. But I don't think that that is in any way essential to the proof. You just would have to add stopping times and it will become incredibly complicated. But that's not the issue. And the second thing is that I mentioned the Ornstein-Uhlenbeck just so that people could get a handle on this, but of course there will be ways of sampling that other than this. The real interest is when phi is not, if mu0 is Gaussian, the real interest is when phi is not quadratic,
Yes,
so that mu is not Gaussian.
Yeah.
Yeah. But in principle, one could apply this to sample from Ornstein-Uhlenbeck bridge using information about Brownian bridge. Yeah.
I think you think it's only growing linearly at infinity if you do anything else locally. So it's not Ornstein-Uhlenbeck.
Yeah, no, I understand, yeah.
No, it is. The quadratic is
No,
Ornstein-Uhlenbeck.
but at infinity.
Yeah. But
Yes, the tails
so if phi of u is exactly quadratic, then
Well,
mu is
that's not
Ornstein-Uhlenbeck.
the case. We're talking
I should stop there. So I want to thank you for my attention, for your attention.
Thank you very much. Are there some questions?
Yeah, I have a question.
Okay.
Andrew, I'm wondering, did you say anything about the rate of convergence of ZD to Z?
No, I didn't get into the proof, but we have some quantitative estimates on some parts of it, but not enough to get a complete rate. That would be an interesting
I was also
question
wondering
to
if
try and quantify that, but there's nothing about this. It's just the method of proof is we prove an invariance principle for the approximation of the noise, and then use continuous mapping from the noise into the solution of this problem. And nothing is quantified at the moment.
Can you incorporate information of phi into the design of
Yes,
the
yes. So that's a good
So the
question.
convexity of the potential should increase
Yeah.
the rate, right?
That's right. So this random walk method, as you're indicating, has no information about phi in the proposal, and one can do much better proposals that build in information about phi into this proposal. So this proposal will, it's only through the accept reject that you'll tend to move to places where phi is small, which is what you want. But as you say, you can look at Langevin proposals and get improvements on this algorithm. So the theorem of Roberts, Gelman, and Gilkes, there's an analogous theorem with Roberts and Rosenthal, which deals with the Langevin proposals. We don't have one for our case, but that would be a natural next step to look at that and other things of that type.
No? Okay, so maybe we can close now this session. And there is a picture now that will be taken outside or inside. Okay. Yes, follow the lady indication. There is the lady.